I'm going to talk about, I think my lectures are the most discrete lectures of the week. I'm going to talk about lattice gauge theories, which is like on the discrete side of this whole topic. So the plan for these lectures, and in particular for the beginning, is to introduce lattice gauge theories, to tell you what they are, and a little bit about how they relate to all these other models you heard about during the week. Yeah, so I guess that's the main thing. So what I'm going to do today, and especially for this first lecture, is just to tell you a bit about what they are first, and how they relate to, in particular, percolation theory. And then also give you some of the tools you will need to follow in the rest of at least my lectures for the week. So I will use the blackboard soon, but I thought I would just show you a few pictures, which are good to have in mind when we talk about these models. So the first model the first kind of family of models I hope you've all seen at least some version of is percolation. And you can study percolation in any graph. And what you usually do is that you have some graph, and these are all done on Z2. And then independently for each item, so the first one is vertex percolation, then independently for each vertex of the model you do something. Either you can think of it as removing the vertex or not, or coloring the vertex in one out of two colors and so on. And the main questions of those models are what is the geometry, what is left? Like how big are typically the clusters? Will there be a connected path from left to right or from top to bottom? And how does that depend on like the shape of the thing you're doing percolation on, or the underlying geometric properties of the corresponding graph? So that is vertex percolation. And I hope you've all seen some version of that at some point. The next family of models, which is also highly related to vertex percolation, is what's called edge percolation. And then you do exactly the same thing. You pick some graph which you like, and then you choose to remove or keep every edge independently with some probability. And you can ask the same questions. Is there a connected component that is big? Like how big are typically connected components? Is there an infinite one? And if there is an infinite one, is that one unique, or is it many of them? Many of them. Is there a connected path from left to right, and so on? And you can do both of these models essentially on any graph. So any infinite or finite graph you like. Typically they are either infinite, or you have a sequence of graphs that somehow grow, and you ask how these properties change when the graphs grow. Do the probability of a connected path go to zero or not? Perhaps even more relevant for the current talk is the model of paquet percolation. And the notion of paquet is slightly problematic because it's not standard. It depends highly on from which kind of angle of mathematics you come. But when I say paquet, I mean the faces of Z2, the two-dimensional faces. They will always be called paquet. Sometimes that's called a two-cell. Sometimes it's called a two-paquet. Sometimes it's called a two-facet. So there are many different names, but we will call them paquets. And you can do the same thing. You can choose to keep or discard every paquet with some probability and ask what the properties of the connected components are. And even though these might seem very similar, and in particular, the first one and the last one, vertex percolation and paquet percolation, are essentially the same on Z2. If you pick a more complicated graph or just a more high-dimensional lattice, they are highly different and very different. So that's models that are good to have in mind. If you haven't seen them before, that's percolation. The next family of models, not in slideshows is better. So the next family of models that's good to keep in mind that's related to all this is the Ising model. Oh no, it's moving. That's really bad. So tell me if it's moving even. Because it doesn't like.
I think it's, yeah.
It seems to be still. Tell me if it's moving. It's a bad thing. So the next family of models that you might have seen before, or how many of you have seen the Ising model before? Most of you have seen the Ising model before. Good. So the Ising model one way to think about the Ising model is that it's one of the easiest way to add some kind of dependency to vertex percolation. So instead of just having all the vertices being there independently of one another, you have some kind of weight, which is a Gibbs measure, which kind of wants neighboring spins or neighboring vertices to have the same, it is picture color, but if you think about them as being spins, which you often do, they want to have the same spin. And then you get the Ising model. And typically what happens is that if this parameter is 0, you don't really do anything, then you still have vertex percolation, because then that whole factor is just 1 for each configuration. But when you start increasing this parameter, you start seeing some kind of clustering. And one of the good things with the Ising model, which is usually one of the things you need to know about if you take a course on it at some point, is that there is some kind of critical magical value, where below that value the model is still quite noisy, and above that value you really get these big connected components. And there is also some more magic to that magical value, because you can look at scaling limits and so on the critical value. So that's known for the Ising model. So if you want to add dependency to vertex percolation, one of the easiest things to do is to look at the Ising model. So one way to think about lattice gauge theories is, the simplest version of them at least, is that we kind of want to do the same thing with edge percolation. So we somehow want to add some kind of dependency to edge percolation. And there are of course many ways to do that. You could think that like somehow you want neighboring edges to kind of align. The way you do that for edge percolation and lattice gauge theories is that you have a weight that's up there. So what that means is that for each plaquette of the model, and remember a plaquette for me is a two-phase or two-cell or two-facet something squarish. A plaquette has a boundary that consists of edges. So now there's those 4 edges. And what this model does is that if we have a plaquette, say P, with 4 edges E1, E2, E3, and E4, the weight assigned to each configuration is that we look at each plaquette individually and take the product of the spins along the boundary of that plaquette. So what the model will want to try to do is to make this product 1, if you think of the spins as being in -1 and 1. So it will try to do the we'll try to make each plaquette have spin 1 if you look around it. So if you think about that in terms of edges here, that will mean that the model will try to make it so that for each plaquette there is an even number of edges in its boundary. So that means that the configuration with no edges, like if you look at the plaquette, it's not more costly to have all edges there than what is to have no edges there. Both are equally, have like the same weight. But if you do that, you get a lattice gauge theory. Of course, that's not the only way to make edges interacting, but it turns out that this is a natural way, given the motivation I will give you later. So this is a natural thing to do, more natural than what it looks at the moment.
What's capital N?
Okay, so capital N is just that, it's a very good question. I will do this formally in a few slides, but the thing is just that as soon as you define a Gibbs measure, you need to, like, if you want to look at the probability of seeing a particular configuration, I mean, you could start with this measure, e to the base and sum over all the plaquettes, and then for each plaquette, look at this product of the edges. And I will do this notation for you later. You multiply the edges in the boundary plaquette. You could start doing that, but if you think about what happens if you sum now over all configuration, it will not sum to 1. And if we want to do probability theory, we really want it to sum to 1, so you need to normalize somehow. And the way you usually normalize is that, like, this is the weight given to one configuration, but then you need to normalize. So what you usually do is that you sum over all possible configurations of edges, and then this thing. which kind of looks fine when you write it up, but then you need to think about this sum, because you kind of want that to be finite. Because if it's not finite, like you're dividing by infinity, and that's bad. And if you think about all the configurations on, say, Z2 or Z4, as I will want to do later, that sum is definitely not finite. So you need to somehow make the sum finite, and the way you usually do that, both for the Ising model and for this model, is that you look at a finite subset of the lattice. So the subset we're looking at will be, and I will write this down again later. So this box, to some kind of dimension, I said P. So the integer lattice, but inside some kind of finite box. So it's just that. So otherwise, apart from, if we don't do that, it's not finite, and then we're in trouble. So that's why. So the problem with this model, when you draw it like this, as you can see here, is that the pictures look kind of the same. It's not obvious that I made something happen when I increased the parameter. So in fact, in this case, like beta 0, then you get packet calculation. So there everything is random, but even when I increase beta, it's not completely obvious that something happened at all. Like you can kind of convince yourself that maybe you see more false squares, like where all edges are present, or more squares where you have no edges, but it's not really obvious that something happened. So on the surface, this looks like a very noisy model. It's not obvious that we added that much dependence by doing this. So the way to think about the model is not really in terms of these edges, because if you do that, the model is far too noisy. So what I did here instead was that I drew all the edges, which had spin, I think, -1, which is kind of the not neutral spin, and then I drew all the packets where this product is -1, which is exactly what the model tries to avoid. And then you can really see that something happens when you increase beta, you get fewer and fewer of these packets. Really fewer. So this is, again, in Z2. It will turn out, and we'll talk more about that later, that the model looks very different if you look in Z3 or Z4. And then you will see even more geometrical patterns, but still now we have some effect of beta. So if you compare this to the Ising model, where you can kind of do the same thing, we'll do something similar. Now the first is again the Ising model. So now remember that we have a start with vertical percolation, and we add the dependency over edges. If you draw like the same thing as the packets, that would be the edges that are now kind of assigned spin -1, the edges where the endpoints of them have different spins. You get something that looks like that. So it looks a bit then like the lattice gauge theory without the boxes. But now you see all these like void places where you have nothing interesting. And one thing you sometimes do for the Ising model, which you might see later during the week, is that you look at the dual of that edges and then you actually see loops. So there is, in the Ising model, when you do this, you already in 2 dimensions see some more geometrical things. And we will see something similar in higher dimensions for this model. But in 2 dimensions, again, this plot is very noisy. Like the packets, there are fewer of them, but you don't really see any geometric pattern there. So this is what we're aiming for. So the goal for my lectures will be to discuss these models, give you some more intuition for them, like how they work and what we want to know about them and how you go about proving that. But before we do that, I will do 2 things. So first, you will give them some motivation, more than like this model we can define. And also, we will talk a bit about discrete exterior calculus, because that's something you might not have seen, and we will desperately need to talk about this model. So first, the motivation, like why people started studying this family of models. And when I say family, I go back just temporarily. The Ising model looked like this, but it has spins in ±1. And some of you might have heard about more fancy models, such as the XY model, for example. It looks very similar to this, but then you have spins on the unit cycle. And you can define loads of families in this model which have the same type of interaction, but you have spins in some other group. You can do that here as well. So that's where family comes from. But the reason this family showed up was that in the 50s, and I think it was 1954, 2 physicists called Young and Mills gave a description of the standard model in terms of kind of mathematical terms, words. And the problem with that, and that was very nice. Like, it was a part of a long sequence of work going through that, so they were just like one part of the puzzle, but that model in physics is called the Young-Mills model. And it's a mathematical description of the standard model. The problem with a mathematical description of the standard model is that it's a description, but it's not a formal mathematical model. It's not even well defined. So it's not really a mathematical model, and they kind of realize this. Like, physicists are well aware this is to some extent a problem. However, to them this description is more of a tool, so it's not very important. Like, it's a problem, but they don't care too much because it turns out that you can use this mathematical description anyway and it kind of works. But it's still a problem, and in fact it's such a big problem that if you solve that and do that formally, you will get $1 million. Because it's one of the millennium problems to make that formal. So it's a big and complicated problem. And then when you have a big and complicated problem, you can try to solve it in different ways. And there are people in this room who tried it, done some parts of it in different ways than what I will describe here. But Wilson in '75 had the idea that maybe you could solve this problem because this is a continuous model. And he thought that maybe you could solve this problem if you gave a discrete version of the continuous model. And then maybe you could obtain a continuous model, which would then be the right one if you're optimistic, as a limit. So he then described it as a discrete lattice model, which turns out to be essentially this model. So that's the first place, technically the second place that it appears there because it's the discrete version of the Young-Mills model. And Wilson's motivation, or Wilson wasn't able to do this. It turns out that this is really, really hard. It's not only that it was a millennium problem at the millennium, which is already 50 years after these models were introduced. It's still a problem. It's still not solved. And it's definitely not solved by passing to the limit of a discrete model. And even though there's been much progress on passing to limits of discrete models and obtaining something, it's a really, really, really hard problem. And I don't think there is anyone working on solving the Young-Mills problem at this point by trying to find the limit of a lattice gauge theory. People are trying to do it, but not in this way. But that doesn't mean that this is a dead model. Physicists are still using it, and essentially for two reasons. The first reason is that you can actually do computations with a discrete model. You cannot really do that with a not well-defined continuous model, but if you have a discrete model, you can make simulations. And physicists kind of like simulations. This is one of the fields where if you search for it on arXiv or anywhere, the risk is quite high. You find a physics paper instead of a math paper where they've done simulations. And they use this a lot. So if you look at arXiv, there are thousands of papers just from the past 10 years. So it's really, really active where they make simulations and make some kind of conclusion. So one reason for that is that you can do it. The second reason for it is that it's not only that you can do it, it seems that simulations of lattice gauge theories give you quite good predictions about the things you want to know about in physics, like the mass of the standard particles and so on. So it also seems that they are useful. They don't really know why, but they don't really care as long as it works, because that's how physics works. If you have a model that's a good description, you're happy. But again, the connection to the Young-Mills model is not exactly clear because no one knows how to pass to a limit. So that's one of the motivations. Physicists really, really care about this model. So hence mathematicians should care. You have a question?
Yeah, how do they do their simulation? Because with the Ising model, you go for dynamic and stuff like
Yeah, so you have...
Can you do this for...
Yeah, so you have two options. Either you can be lazy, and for the simulations I did, I was lazy. So I just used a deep sampler, which is slow, but it works. And some of them, most of them, I think, still do versions of that. And there have a few other, slightly more advanced models as well, but essentially a lot of them, especially in the beginning, use just Glauber dynamics. But then there's a recent paper by Franken and Steinhardt. I think they're now in the US somewhere, and the other one is in Tel Aviv, I think, who has a random cluster model for this. and with the Swenson-Wang dynamics, you can also do that. And that speeds it up a lot if you're willing to take the cost of learning algebraic topology. But that's the options. So essentially, to some extent, the same as for the Ising model. But you have to kind of translate and rethink everything. So the other place it appeared was actually before Wilson introduced it, in a paper by a mathematician called Wegener in 1971. Because by then, people were studying the Ising model quite a lot. People are still studying the Ising model. But they were studying the Ising model, and they had realized that the Ising model has a phase transition. But the Ising model also has another property, naming that it has like a global spin flip symmetry. So you can flip all the spins and essentially get the same Ising model. Because then like the edge weights will be the same. And a question at the time was, if you have a model with a phase transition, is like, can you also have local symmetries? Because at the time that wasn't obvious, because the Ising model, like you cannot simply flip the spin at one side, because then all the weight, the weights change. So they wondered, like, is there some model which has some local symmetry that also has a phase transition? So these models were also introduced as an example of models that had a phase transition and local symmetries, which we'll discuss more later. So it was also introduced in the mathematical literature in 1971. And Wegener didn't really prove that it had a phase transition, but he argued that it should have one. And then there were several later papers that actually confirmed that it does have a phase transition. So that was the very brief introduction. And I will define these things more formally maybe in the next lecture, and also tell you a bit about what people are interested in. But before we do that, to make my life simpler, I will give you a kind of crash course into discrete exterior calculus. So these are the things I want you to know about before we continue. So I will tell you about what cells are and what chains are. I will tell you a bit more about boundary operators, how to go from paquets to edges to lattice. We will talk about what a loop is, and what an oriented surface is, and what that is relevant for loops. Then I will tell you very briefly what a form is. And then we need discrete derivatives, and we will need a version of Stokes' theorem for discrete calculus. So a lot of this will be kind of analogous to what you might have seen in exterior calculus in your calculus course, but on a discrete lattice. So this is mostly because my life will be simpler if I can use this notation, so I will teach you the notation. Does that sound right? Is this a razor or this an eraser?
So there's the wet one, that's normally used.
I don't know.
But, oh, that one. Maybe
Yeah, but that's also very wet.
That's good.
Yeah, it is so much better. So the plan is to do this, and then maybe after coffee we will talk about the basic properties of the model and what we want to know more about. So we need to define those things, and my first task will be to try to make the slides disappear. That would really, yep. Yeah. They also told me sitting in the basement doing the magic. So I'm not sure it was me. So we need to define those things, so you know what they are. We will throughout work on a lattice. And I've seen people work on other lattices, that's something you can do. But we will always work on a lattice, and when my work on lattice gate theories, I usually been interested in Z4. And the reason people are interested in Z4 is that if you're a physicist, you usually have three space dimensions and one time dimension. And that in total gives you 4 dimensions. So if you have discretization, you have 4 dimensions. Now, there's quite a lot of literature on other dimensions as well. Usually, in this case, Z4 behaves kind of like Z3 and Z5 and Z6 and so on. But Z2, where you could also define the model, behaves quite differently. But it's still like an interesting model you can study, but it's very different from the other ones. So I'm saying Z4, but it's fine if you think Z3 because that's easier to think about. But essentially any dimension that's higher than 4. And then, as we said earlier, defining Gibbs measures on infinite lattices that's bad and complicated. So what we usually do is that we look at this finite box, which was again, oops, I don't want to write again. I want to write -1 to n. Before dimensions. So that's the lattice you want to work on. So it's a finite lattice, and I will not care too much about what happens on the boundary, although that's definitely something you could care quite a lot about. So that will be the lattice. Now in 4 dimensions, you could have a number of different geometrical objects, like the smallest possible ones. And there are different ways to denote them depending on what kind of topic you're coming from. If you're coming from algebraic topology, you might call all of these plaquettes, which makes things very confusing. But if you're coming from discrete exterior calculus, you usually call them cells. So there are 4 different types of cells we need to care about in set 4, and we don't care too much about most of them. So the first ones are what's called 0 cells. Another word for those are vertices. And they will be denoted by C0 of Bn, so all the 0-dimensional cells of Bn. Then we have the 1 cells, which I will usually call edges. They are 1 cells, we will write C1 of Bn. And then I will also care about the 2 cells, since the model is defined on plaquettes, which will usually be called plaquettes, which will then be denoted by C2 of Bn. And to be able, if you only care about spins in ±1, if you only care about the Ising model, these do not need to be oriented. But if we want to be able to say something about what happens for a more fancy group, these all, including the vertices, need to have an orientation. And as long as we don't worry too much about the higher dimensional cells, it's not that complicated. It's very easy to think that an edge could have one of 2 directions. Either it's going in that direction, or it's going in that direction. And if this edge is called E, we will call this edge -E. Plaquettes, it's not as obvious how you would define an orientation of, but we think of them as having either that orientation, like either being a counterclockwise plaquette or a clockwise oriented plaquette. And this will matter when we talk about the boundary of them. That's mostly where it appears. So they can also have 2 orientations, and again, if this plaquette is P, this plaquette will be -P. So they really come pairs. Vertices is more sketchy. It's not really obvious how you define the orientation of a vertex. It's not very, very important what the orientation even means. We just note that we have 2 copies of each vertex, and we say that one is positively oriented, another one is not, and it doesn't really matter what it means, just to make it consistent with everything else. So that's the cells we need to think about. Now, there are several different ways to do this, like formally, up to any dimension. But it will not be very important here, and I don't want to go into the formal definition from this focus. But you can do that. So that's cells. So the notation we need to think about are these 3. The next thing that will be nice, if we want to use discrete derivatives, is to define something called chains. And chains is just formal sums of cells. That's the only thing it is. So it's formal sums of cells of the same dimension. So you could, for example, the chain is a formal sum of, say, k cells, that is cells of dimension k. That is called a chain. And when I say a formal sum, that could, I guess, technically be weighted by a lot of different things, but in this case, we think of it as being a sum with integer coefficients, so you can really think of it as having some number of copies of each cell. So one example could be like E1 plus E2 minus 3 E3, for example. That would be a chain. So any type of formal sum of cells is called a chain. And the main motivation we will have for defining chains, or the main place where it appears, is that I will later, quite soon, be very interested in loops. And then I mean loops of the lattice. So then the main point is that any loop or path in general in the lattice can be thought of as the formal sum of the corresponding edges. So that is our main motivation. So if you have some kind of loop, and now I don't want it to make it very long, because then we all need to be here forever. But if I, for example, have a loop, this is one, and we have edges E1, E2, E3, E4, E5, E6, E7, and E8. And this is the loop gamma, which you might think of as a loop. We can actually formally think of gamma as being the sum of these edges. E1 plus E2 plus, and all the way up to E8. So that will just be nice when we talk about the rest of the. So as long as you have some kind of geometrical object, instead of thinking of that as a set of the edges in its support, we think of it as the formal sum of it. So it's really just a formal thing. It's not really something you need to understand on a deep level. It's just like, it will be nice if you do it like this. So as long as you have a formal sum of K cells, that's called a K chain. And we will let C, and now the K is up there, and this is inherited somehow from discrete exterior calculus. This will be the set of all K chains with integer coefficients equal it. So the simplest possible K chain you could have would be the trivial one, the one that's the sum of nothing. That would be a very boring K chain. And then every, say, edge would also be a K chain. It would be one chain, because it could be like a sum of one copy of that. Yes?
Will you let the cells to have the natural orientation induced by Z4 or just?
So I will have 2 copies of each edge. One with each orientation. So it's a trivial but boring solution to it.
I mean, like the positive orientation is the one that is
going to the right. Yeah, sure. So right and upwards and in the increasing direction. So that's the K chains. The next thing we will need, maybe I can fit that. Maybe I'll just change the board. The next thing we will need is boundary operators. And this also works for all K cells, but we really only care for one cell and 2 cells. So if P is a 2 cell, we let, or like we use that to denote the boundary of the cell. And the boundary now, if that is a 2 cell, is supposed to be 1 cells. And for a plaquette, it's exactly what you think. It's like the edges in its boundary. The only kind of strange thing now is that since I don't really like sets of things, this will be a chain. So with partial P be the one chain. Corresponding to its boundary. And here we need to worry a little bit. Not too much. So if we have a plaquette P and it has an orientation, you can now see that that works quite well with the orientation of the edges. Let's use color. Green is a nice color. So it's quite natural that this has 4 edges in its boundary, namely these 4s. And if we orient them in the same way as the plaquette is oriented, we get the correct orientation for the boundary. So in this case, if that is E1, E2, E3, and E4, that means that the boundary of E should be E1 plus E2 plus E3 plus E4. So it's really not doing anything strange. The only thing that might be a bit strange is that it's now a formal sum and not a set. But since these are like fundamentally different things, the formal sum is really just a formal thing. It doesn't really do anything. And we can do this for edges as well. So if E is E, now that will be 1 cell, it's an edge. We can do the same thing. To again be its boundary, but now to make this notation make sense, if this is an edge with an orientation, that's a 1 cell, so the boundary is supposed to be 0 cells, that's vertices, which kind of makes sense. We have 2 vertices, we have that one and we have that one. And if this is V2 and this is V1, we think of the boundary as being that one minus that one. And again, this all kind of makes sense if they are both positively oriented. This you can all do this formally using either discrete theory calculus, or you can define it from algebraic topology and so on. But if we do that more formally like this, then that will take a week. So I won't do that. But I hope this is fine, because this is the only case where we're going to down that later. The only thing that might be useful at some point is the co-boundary, which is kind of the opposite of the boundary. So the co-boundary, if I can spell it, it's denoted by almost the same thing, but we put a hat on top. And defined by, so if you have, say, a plaquette and an edge, say you have an edge. So the co-boundary of the edge, it's supposed to be the formal sum of all the plaquettes, like we go up a dimension, that have this edge in its boundary. So we can write it as a sum now. So the sum over some number of plaquettes, and I want the plaquettes such that I want plaquettes such that E is in the boundary of that plaquette. So in 2 dimensions, that would mean that if this is the edge, then that's in the boundary of that plaquette. So let's say this is P1. It's in the boundary of P1, and let's make this edge go downwards. So it's in the boundary of P1, and it's also in the boundary of P2, and for that to be in the boundary of P2, P2 needs to be oriented in a different way from P1. So it would be the sum of those two brackets. So just a formal thing. And this, now when we have a boundary operator as a formal sum, it's very easy to write down this definition. And this works in any dimensions. You could also think about, say, if we have a vertex instead, and is interested in the boundary, this will be in the boundary of all the edges that kind of ends at that vertex. It will be in the boundary of this one, it will be in the boundary of that one, and of that one. So the boundary maps to self, to its boundary in the way you think. It maps from a k cell to a k-1 cell, and the co-boundary does the opposite. So you could also think it as like the co-boundary, in this case, gives you the formal sum of all the packets that are kind of affected by the spin of E in this model. So that's why it's called that.
And here you have like P1 minus P2, right?
No, because I gave them opposite orientation. But you're completely correct. Like if I would have changed the orientation of that, that would have been the case. But I gave them both the same orientation as the edge.
I see, because in that convention you had a minus sign
Yeah.
with the same letter
Where did I do that?
in the two cells picture.
Oh, yeah. So then I called it minus something.
Right.
Yeah. It was just a name. I was thinking of it as a name.
Yeah.
But but you're correct. So if that one, this one in this case is positively oriented, and that one is negatively oriented. So the main important thing is that we keep the same orientation for the boundary and for the thing we started with. So now we have boundaries, we have cells, and we have chains. So the next thing I listed was that forms. I think it must have been forms. So now we want forms. And forms will essentially be functions, because now we have something to work with. We have a lattice and we have a lot of notation for the lattice. Now we want functions. And we are not interested in all the functions, and we want a function that maps a cell to a number or group element or something, and we're not interested in all of it. And I will do one forms first. Okay, let's see, we do three forms. So this form is a function from the set of cells, so K cells, to a group G. And for the rest of the week, G for me will mostly be set to. But if you talk to some of the other people in this room who worked on these models, G is much more complicated. It could be U of 1, if you talk to Christoph later in the week. It could be SU of N, if you talk to Hao. So it could really be a more complicated group. But it's a function from a set of cells to group G. That is, for each cell you assign a group element, such that we always have maybe I should have called this something. Let's call it, it's a function, you can call it f for now, because why not? So it's a function so that we always have f of minus c. So we know f of c and wonder what f of minus c is. And minus works because this is a group. And I will use the notation for an additive group now. Is equal to minus f of c. So that means that the group elements assigned to edges, and like an edge and the negative of that edge is always coupled. One is always minus the other. So for example, if the group would have been U of 1, And we kind of think of that as the interval from 0 to 2 pi, assigning an angle to everything. Or group elements to as I, like that. Then f of minus c would really be something different. So that it would be minus theta if f of c was equal to theta. But if the group is set 2, which is more simple, then these elements would really be the same, because in set 2, minus 0 is 0, and minus 1 is 1. So we will not see so much of these in one forms, but for more complicated groups, again, we would really see that this was important. So for set 2 minus group element is the same as the group element. And now I haven't lost the thing. So I'll erase this. So this is mostly to be able to have more complicated groups in mind. So for G equals to Z2, and any group element, we have minus D equals to D. So that's just something to keep in mind. But it's important to have that if you want to work with essentially any other group than Z2. Say Z3, then you would already need to care about this. So that's forms. So it's functions that assign some kind of group element to each cell of your dimension of choice, say 2 cells and 1 cell something, would satisfy this thing. So we have 2 things left. We have discrete differentials and we have Stokes' theorem. So we need to define the derivative of a k-form. Yes?
Is there a direct analog of this in the continuous setup? Because there, I would think, well, one of our k-forms would be the algebra element.
So there are a few experts on continuous things in the room.
Be legal value, right? Usually lattice gate theory should be legal value.
Yeah. Yeah, but if you do it in the continuum, you call the continuous space or it's harder, I guess, in continuous space because then it's not obvious what the difference between things. Like it's harder to talk about cells in a higher dimension because then what is really like how do you distinguish, say, a point from an edge from a packet?
Yeah, I guess you would have some like g-valued chronology, but then I thought it's like more like in a whatever.
Yeah, no, but it's a good question, but I am actually not sure.
You need some cellular decomposition of some continuous space and then...
Yeah, but then again you have then kind of cheating because you're making it discrete.
Yeah, exactly.
Yeah. So the last thing we need, which will kind of connect back to the continuous setting, is some kind of derivative. Okay, so take one thing first. So we have forms and we have cells and we have boundaries and stuff. The reason we want this to be sums is that now everything works quite well together. So if say this is C. If C is a chain, remember that was the formal sum of cells. Then we can define the boundary of a chain, which is kind of nice. So boundaries were defined for cells. But say that this C is a chain, say it's a sum of E1 plus E2 minus E3, for example, for some edges. That would be a chain. To keep in mind. Then we would say, we could talk about the boundary of C, and then that would simply be the formal sum of the boundaries of these things. And since everything is now sums, this actually works. So one example would be, say that I have 3 packets here. And these are P1 and P2 with, say, this orientation. So they now actually have the same orientation. That's fine. And say that the chain is P1 plus P2. Then I could use the the boundary operator directly on that thing. This was a formal sum. By linearity now I will get this. And if we think about what that is, because that will be important in Stokes' theorem, this one has this edge in its boundary and that edge, and let's add an edge here, so they get one each, and that edge with that orientation, which is kind of fine. The other one also has 4 edges in its boundary. It has that one, that one, that one, and that one. So now you see those two are kind of the same but in opposite orientations, so they will cancel. So if this is E1, E2, E3, and E4, and we say that this is E1 prime, say, E2 prime, E3 prime, and E4 prime, then E2 prime and E4 will cancel because they are the same but in the opposite direction. But what will remain will be E1 plus E2 plus E3 plus E3 prime plus E4 prime plus E1. So things like that can happen, but you can apply boundary operators to chains. So the derivative is essentially what happens if we try to apply the boundary operator to a form. So I think that's the last thing I'm going to say before we get coffee, which I guess we all need by now. At the end of the crash course. So we want a derivative, and we kind of always want a derivative when we do calculus, because otherwise it's basically no calculus. So the discrete zero derivative, we will call that D when we think about it as an operator, D like in derivative. Of a K form. We should call it something. So the name now will be F. It's very tiny over here, but it's otherwise. So we have a K form. That was this function with this odd property that it connected edges with opposite edges, packets with opposite packets. If we want to take the derivative of that, that is defined by F, I call it F, sorry. So the form, I wonder what the derivative is. It should be another form, or another function, so we think about this as being something we do look at in some cell. Say we'll look at it in a packet. What that is essentially F of, if F is a one form, we want to take the derivative and get a two form. And then the question is, how are these going to relate? And the way they're going to relate is that we're going to sum over the edges in the boundary of P and look at the formal sum or the sum of F of E. And F was a function, so this is the sum of elements of the group, which is fine if it's an additive group. If it's not an additive group, you have to think and be slightly more careful in general. But if it's an additive nice group, then you're fine. and a billion. So this is how you define the derivative. So if that you started with the one form, or this thing will be a two form. And the value you have at each bracket of the two form df will be the sum of the elements in the boundary of that bracket. So that will map from one forms to two forms. And you can always do that. And you can do the same for edges. If you start with something that is a zero form, you can use this operator to get a one form that is something which has a value at each edge by summing over all the vertices in the boundary of E and looking at f of V. That would map from one forms to two forms. So this now, or zero forms to one forms. You can always use this to get something of one dimension higher. And the main reason, and the other way to write this, if you're sloppy and like chains, this is one of the nice things with chains, is that people usually write this as f, like the form evaluated at the boundary of P. That makes the formula much simpler. And here in the same way, that will be f at the boundary of E. And then you have to be slightly careful about what orientation the boundary has. And now what's nice with this whole setup is that now we will essentially get Stokes' theorem for free. So if you remember your first calculus course, or maybe the second, when you did Stokes' theorem, there was some work going into Stokes' theorem. But in this setting, there is very little work going into Stokes' theorem. Because everything now is kind of linear. We extend everything by linearity. So if Q is a sum of packets now, because I wrote two. This works for any k, maybe we should just write k. If that is a k form, no, if that's a k chain, so it's a formal sum of k cells. Then by linearity, we get a discrete differential evaluated at Q. So that is the formal sum over all the, so like the value of df at all the cells in there. That is df of Q.
Boundary Q?
Not yet, because I have the delay. Yeah. It will disappear very soon. I will do what you think very soon.
Yeah.
This will be the sum over all edges in the boundary of Q, exactly as you thought, of f of E, or if you want to be extremely brief, f of the boundary of Q. So this, since everything is linear and nice, if you have some kind of chain that is a long formal sum of something, instead of evaluating differential, there you could look at the function as the boundary. So what we'll do first after the, and this is Stokes' theorem. This is exactly Stokes' theorem from analysis 2, say, whatever it was called where you did your undergraduate studies. Is Stokes' theorem. So the first thing we'll do after the break will be to return to the definition of lattice gauge theories, and now give the definition in this language, because that's what's usually used, and then say something about where Stokes' theorem appear, or why that's relevant. But now I think it's definitely time for coffee, right?